Come to Brazil, Bruno, come to Brazil. Come to Brazil, Bruno, come to Brazil. Come to Brazil, Bruno, come to Brazil. Come to Brazil.
I come Brazil.
Good morning. So, in a few hours, Megan, Fabio, and I will be really relieved that nothing else will happen, I hope. So I have 3 announcements today. So the first one is that we will take a group picture just before the town hall. So if you want to be in the group picture, please come to the town hall, okay? And you are not there, that's okay. The second announcement is that some people is organizing the first person meetup of disabling computing. This is for people with chronic illnesses, mental illnesses, and neurodivergence. I may not share the way that people talk about disabled people, because they don't believe they are disabled, but that's my personal comment. And they will meet today at the lobby of the hotel and go to a nearby place at 11:10. So if you want to be there, 11:10 in the lobby of the hotel, and the organizers of the meetup will take you to the right place. And the last topic is a bit important topic. We sent an email about it before the conference. Fabio talked about this in the beginning of the conference, and we will talk, I guess, about this also in the town hall, but please try to think about your security. We recommend not to go to the north part of the city, and if you want to do so, and I understand you perfectly because I'm a researcher too, I want to see everything, go with locals, but let's not try to go at night because you need to be careful. For example, also, I have told many people just being 15 minutes in the entrance of the hotel to take their badge out. If you wander with the badge, you are saying, I'm a foreigner. So it's like, and also they can approach you and tell your name. So, hey, Meg, how are you? When was the last time you came? And they say, why? Well, you are in your name. So please try to think outside your safe zone, in your very safe location. And this was the same I got in my first conference when I was a PhD student in the 80s in Chicago. And I was at the university, and the person local said, don't go south. If you go south, it's your problem. You are an adult. We are not responsible. So here is the opposite. Don't go north, okay? Thank you. And Alexandra will introduce our wonderful last keynote here.
Good morning, everyone. So a lot of the work in our community is about foregrounding and mitigating harms, challenging power, but also about asking for more rigor in AI research and practice through better documentation, better problem formulation and terminology, better engagement with stakeholders, better development practices, better understanding of impacts, and critically, better evaluation practices. I think Sanmi's work is an excellent example of this. And Sanmi Koyejo is an assistant professor in computer science at Stanford University, interested in the principles and practice of trustworthy machine learning. Please help me welcome Sanmi.
Hey, it's a real pleasure to be here. My title changed, as many of you might have noticed. This is one of those things where I had this big sprawling talk planned, and then at some point at 2 a.m., I won't tell you which 2 a.m. of what day, but I changed my mind and decided to focus a little bit more on a couple of papers that I think are interesting and speak to some questions that I think are interesting within the community. You have a chance to maybe judge whether my decision-making skills are good at certain weird times of the night. But hopefully this is an interesting talk for you. So for those of you who may not be aware, the idea of sort of scaling in language models and AI generally, but specifically in language models, really are animating so much of the conversation, both in research in terms of how we think about the practice of building, growing language models, but also questions in governance, questions in policy. A lot of these are quite strongly driven by questions tied to this hypothesis, maybe observation, that as you scale up models, they get better, and they get better in sort of meaningful ways that drive some of how we should think about what we're doing in the field. So I'm showing here some examples. I won't go into detail, but again, this idea, both within the community, but also broadly, I think, in society now, that the scale of models is critical for thinking our mental models of what the AI tools, language model tools, machine learning tools are doing. And so for those of you who either haven't had coffee or will fall asleep right after this, here's the talk. So here's the sort of key idea that I hope you take away from the discussion today. So the main point will be a observation, a claim that metrics, which are part of our measurement enterprise, play such a key role in what we think about in terms of predictability of large language model performance with scale. And in some ways, this is a small problem. In other ways, it's a big problem in a sense that, again, it's animating so much of our field. But I think some of the discussion here will hopefully inform how we think about these questions. I'll present two papers primarily, one old, one actually quite new, where I think the archive hopefully is out by the time we're done with this talk. So literally work hot off the presses. So this will be the first presentation of some of this work. The key point that I'll make on measurements and metrics is that some of the metrics we pick, often the preferred metrics that have become the standard way we choose to measure large language performance in the field, end up systematically degrading predictability. And I'll explain what this means in a couple of slides. And I'll also argue that partial credit and probability score metrics are more predictable. And I'll hopefully give some larger points about why I think this is interesting and meaningful. Okay, so a quick primer, just in case you're not familiar. It is possible that some of the folks here are not familiar with some of the ongoing work in NLP broadly, large language models. I'll just briefly mention this. So as many of you might know, the key technology in training large language models is next word prediction. There's a few things after that we think also matter, but a huge chunk of what goes into constructing, training large language models is this idea that we sort of remove words from sentences, typically data on the internet, and then we train a machine learning model, some kind of sequence prediction model, to fill in the words that we've taken out. So some of you might know things like Mad Libs. If you're familiar with that, it's a good analogy. If not, it's a terrible analogy. But otherwise, the idea is we're filling in words. This is, again, the key bit of how we try to build large language models. Beyond this initial training, which is, again, this filling in words, there's this observation, or at least practice, that models once trained in all the ways that we trained them and deployed can be useful for lots of different kinds of tests. I'm showing here blurrier than, but again, this is not important. The point is to show there are lots of different things people use them for. This is from OpenAI at some point, where they've been sort of suggesting or arguing or maybe deploying tools from large language models for lots of different applications. I think the question of how we choose to do evaluation is kind of interesting, and maybe I'll do a brief aside for some of how this practice has shown up over the course of time. I think it informs a lot of what we end up doing when we're sort of measuring machine learning models. So benchmarks are really quite key in what machine learning and AI is now. The key idea, and a lot of what has driven machine learning, I think meaningfully separately from closely related disciplines, say like statistics, is we care a lot, in principle anyway, about measuring the artifact at the end. And as many of you might know, the standard idea is that we hold out some data after we train models, and we evaluate our models on this held out data. And unlike many other fields, we actually don't care that much what you do when you're training your model. So I think this is a meaningful sort of conceptual difference in the machine learning field. And I say don't care in the sense, there's good practice, there's actually getting the thing to work. But unlike, say, statistics where the key outcome might be inference, and the specifics of the model you're training, what the parameters mean is sort of considered quite meaningfully important. Often in machine learning, do whatever you like. As long as you can show something on some held out data set, which we take as a proxy for how the model might do when deployed in the real world, we're happy. And again, I think this drives so much of the practice. Different names for this. I saw a keynote from Moritz Hart recently, a few months ago. He called this the iron rule, so I just mentioned this here. Again, this idea that sort of the evaluation or benchmark bit of this is so critical for how we think, build, deploy machine learning models. Another little bit, I just think this is interesting. Part of this is adapted from a fascinating paper I read from this FAcct, so I just wanted to mention this. I don't believe the authors are here because this, I think, was a virtual talk, but if they are, it'd be great to chat a little bit. So it's called AI as Sport, the Competitive Epistemologies of Benchmarking, where they go through some history, but also infer from that something about what this implies for, again, the practice of evaluation in the field. But for those who are interested, part of the history ties to work in the 60s on OCR, where data was collected for character recognition. And this ended up being shared widely and being used as sort of this first idea of a benchmark, things that were common across researchers that people used to measure progress on some notion of some task performance. AI went through a bunch of ups and downs in terms of public perception, and part of this led to some effort in the 80s from DARPA, what they call the common test framework, which is some standardized way of evaluating AI and machine learning models, countering the argument that was made quite strongly at the time that we mostly told stories as a field as opposed to sort of meaningful evaluation of tools. And so there was the idea to standardize things. This ended up in this benchmark tool in the 80s. In the 2000s, the Netflix Prize ended up, I think, really entrenching within the broader community this idea of sort of benchmarks as sport, benchmarks as sort of this common practice within the field that drives how we evaluate things. Netflix Prize, Netflix's company does video recommendation. They had this $1 million prize to try to predict something tied to preferences for movies. The fun anecdotes here, as many of you might know, they actually didn't end up using the results they paid $1 million for many reasons. It ended up being too complicated to actually implement within the framework. It turns out also the question may not have been the right thing. Questions on predicting how a user might rate a movie in terms of mean square error may or may not directly correlate to preferences in terms of selection for movies. Also, the measurement practice changed quite a bit under the hood from when the competition started to when things actually got deployed. So lots of fun stuff there. They actually completely changed a lot of the tooling behind the scenes. But again, this I think really had a big impact on how the field engaged with measurement and benchmarks. In the 2010s, we had ImageNet. Again, the field coalesced quite strongly around this idea. And I'd argue now we're in another version of this. So in lots of work in large language models, in other aspects of sort of large-scale AI, but specifically large language models, there's now a sprawling set of benchmarks. I think maybe meaningfully different from some of the historical work on this is that there's many more benchmarks posited to measure different aspects of what it might mean to build good large language models. But again, lots of activity, lots of interest, again, driving a lot of what we think of as progress in the field. Enough so that, whenever large companies deploy some new model, they spend quite a bit of effort talking about some result on one of a few key benchmarks and sort of tout this as progress in reasoning or some other aspect of improving how we build large language model tools. So, it's worth saying a bit about what a benchmark is. So the key first step in a benchmark is to pick a data set. You combine this with some kind of metric, so something that measures some notion of what performance might be on this data set. I'll maybe go through some examples if you're not familiar. There's some norms generally that go around this. The norms vary and can be messy and complicated, but I'll just say some practice around this idea of data set and metric, and this combined is, I think, a meaningful cartoon model of what it means to construct and deploy a benchmark. As mentioned, there are now lots of benchmarks out in the community. I'm showing here mostly examples in large language model world. They share a few characteristics. Often there's some goal to measure some aspect of model performance. Generally, there's some analogy to some notion of intelligence. I think there are meaningful questions on construct validity that I won't spend a lot of time on, but I think are good for the community to engage with. I'm citing here some work, for instance, by Raji et al. That engages with this question of what we say these benchmarks are measuring when we say they're measuring something. And so can I, for instance, say something about language understanding based on some data set? How true is that connection? But again, the premise, or at least the key ideas here again, data set, some notion of measurement, some norms around what it means to measure, and this becomes a benchmark, and this gets scaled up. Beyond specific benchmarks, there's now, again, more and more this idea. They're I think, somewhat confusingly also called benchmarks, but I'd call them sort of meta benchmarks. We need a better name if someone has a good idea. Feel free. But these are these sort of collections of benchmarks that typically will combine a bunch of different data sets and a bunch of different kinds of evaluations together to capture some larger notion of what it means to train, again, better models. So I'm showing here an example from Stanford, from my colleague Percy Liang on HELM, Holistic Evaluation of Language Models, which has a bunch of different scenarios they're positing that ties to a bunch of different tasks, a bunch of different metrics, a bunch of different notions of perturbation, often to measure various kinds of robustness, capturing hopefully meaningful notions of what it means to make progress on training large language models. We've also done some work in this space. So I'm showing some work we did last year, presented at NeurIPS, that tried to engage with this question of trustworthiness within large language models. And so we posited a few different perspectives, again, did the same thing. So a bunch of different evaluations. So data set, metric, some kind of norm around it, and this was some notion of measurement that we hope to engage with this question of how we build more trustworthy large language models. Okay, so that's one of the key ideas important for the discussion today. Another key idea, and again, hopefully summary for many of you, but if you haven't seen it, hopefully I can briefly touch on these things, is this question of what scale means when we're building machine learning tools. So again, this is one of those things that it's really hard to overstate how much of an impact this idea of scale has had on modern practice of building machine learning models. So some of this ties to early literature, but some of the modern instantiations include work by Hessness on some empirical notions of predictability across scale. The intuition here is that if I take some large compute platform, or compute platform, some data sets, and I scale things that are easily scalable up, generally scale means I scale up training time, data set size, model size, a few other things, that I should expect my models to get better. Typically, and originally, better here meant the test loss. So if I have a training set, a test set, the performance in terms of test loss on the held out test set should get better as I scale up the things that I can scale. It's worth mentioning that, again, this is one of those cases where the story is big. There are specifics in terms of details that we don't always mention. There's a bit of lack of specificity in terms of exactly what we're scaling and how, but I think the large-scale trend has seemed to hold, and again, has driven a lot of both in terms of industrial practice. So for instance, how we think about what it might mean to make bets on what models might do better in the future. So this idea that scaling might be such a big driver that we can mostly rely on scaling to think about how to improve models. All the way to, again, what I've mentioned briefly on questions of governance and policy tied to models. Some of this thinking is also tied to, I think, some quite interesting, if you haven't seen this, is worth a quick look. Writing by Rich Sutton. This is in 2019, where he talked about what he called the bitter lesson. I'll just briefly read the first sentence. The biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective and by a large margin. Again, anchoring on this idea that scaling in terms of here compute often taken as a proxy for other things, data, a bunch of other things that we can tweak about increasing large language models are what drives so much of what we might think of as progress in the field. Of course, as mentioned, this story can be a bit more complicated. The initial plots I showed on this last slide were what are known as the chinchilla scaling laws. The detail is not important other than they made certain choices in the design that drive what they showed in the results. There have been subsequent work probing various aspects of this question. So I'm showing here on the left questions on whether the scaling laws might change meaningfully if I predict, maybe subselect data samples and do different kinds of strategies like data pruning. This seems to qualitatively change the results, but we still see trends that, 2D trends where by eye we can make, I think, strong inferences about what we think might be happening. Also work asking questions about data constraints and maybe repeating how many times we go through a data set. Because the data sets are so large, often one does very few passes of a data set when you're training large language models. More recent work has tried to engage with this question of training over multiple rounds and seeing what happens. Again, we see trends. These trends seem, this low dimensional figure where we can tell simple stories often show up. So this, I think, is some of the key background for some of what I hope to talk about today. So all of what I talked about was mostly background, but hopefully, if you're not familiar, you're sort of up to speed. The key story today will be asking questions about task performance, so some measure of how models' performance on particular tasks measured by particular metrics, what they look like when we scale model sizes. So this is a combination of this idea of scaling, which I already mentioned briefly, where the original thinking of scaling was mostly about test loss. So cross entropy, which is the primary measure of data fit for a language model. And then downstream benchmarks, which are posited again to measure various aspects of downstream performance, often again via analogies to notions of intelligence, for instance, within models. And so this talk will mostly try to combine these ideas together and ask questions, not about cross-entropy predictability, but now about downstream performance predictability. So there's somewhat recent, but I think fascinating literature on this. I'm showing here a couple of talks, a couple of papers. This is around 2020. One of the directions that I think got some of the community quite excited was this observation that while there did seem to be some trend lines for certain kinds of evaluation. So on the left, we're looking at various kinds of arithmetic tasks that are done using large language models. So I'm showing addition, multiplication, I think lots of interesting questions about why this may or may not be a good task for a language model. I think a lot of the motivation here is primarily the intuition that the ability to solve various kinds of arithmetic tasks requires some notion of planning. This suggests something about intelligence if large language models can do this effectively. And so this is something that I think is often quite exciting to folks thinking about this question of improving models. On the right, I'm showing evaluation over a large set of, again, this mega benchmark, where there's a bunch of different tasks, things like unscrambling words, question answering of various kinds, and the like, which was posited to illustrate what were later called emergent abilities. I'll talk about this a little bit more in a second. But the key thing here is, some notion of trend. I think some of what animated a lot of the discussion here was change in model performance that seemed somewhat unpredictable. Trend was there, but exactly when models would go from quite bad performance to all of a sudden what seemed like good performance with scale seemed harder to predict. And I'll touch on this in a second. More recently, there's been quite a bit of engagement on this topic. So there's work, for instance, looking at whether the predictability arguments really hold. There's some work suggesting that perhaps it holds, but only beyond a certain scale. So sort of when models do small, it's hard to do. Maybe big enough, we see clear trends. There's work suggesting similarly that sort of the scaling argument seems to be a key driver for what we can say about predictability. We've done a bit of work on this topic, so some work out of my group from Bear Van Issyk, where we looked at translation tasks. I'm showing on the left cases where the trends were much more clear. Here we're looking at translation between languages. We vary the pre-training, so in pre-training we mix different languages together, and in evaluation we use some of the standard translation evaluation metrics, things like blue score. The key here again being we're measuring something that is not the same and in fact behaves a little bit quite differently, meaningfully differently than something like test loss, cross-entropy loss. On the left, we see cleaner trends. On the right, we have examples where trends are much less clean. Our argument is some of the general story in machine learning about distribution shift and how correlated the train and test sets are do seem to play a key role, and I think may have been underappreciated in a lot of the discussion about scaling so far. Here's some other work from my group in prep by Brandon Miranda, asking similar questions, but again, driving this argument of data alignment playing such a key role in predictability. And so this motivated us to ask this question of why is predictability of downstream performance somewhat elusive? So in terms of, again, test loss, there seem to be quite strong I call it a scaling hypothesis. The community calls it a scaling law. We can debate that offline, but it does seem to hold. This does seem quite credible and strong over lots of replication over lots of different people. So this seems a real thing. But when we go from cross entropy to some kind of downstream evaluation, it somehow just gets messier quite quickly. And so this motivated some of what we've tried to work on this topic. And so in this talk, most of what I'll talk about is one of the choices that you make when you build benchmarks, which is this choice of metric. And I'll tell a couple of stories about how much this metric choice can influence predictability and downstream performance of large language models. So I'll talk first about this paper called, full credit to Ryland, first author in this work. He is a genius at picking titles. I think title picking had a big influence on how this work was received. Some of it was also maybe timing. But it's titled, Are Emergent Abilities of Large Language Models a Mirage? And we're fortunate to be recognized by NeurIPS as one of the outstanding paper awards last year. And the key idea in this paper, one of the key ideas, is that discontinuous metrics, things akin to accuracy, things like exact string match for various kinds of downstream evaluations, explain a lot of what we call unpredictability in language models, downstream performance, tied to what has been called emergence. So to frame this, it's worth mentioning briefly this idea of emergence and LLM capabilities. So the story, emergence, like many things in the community, like maybe I've alluded to a few times today, is not that well defined, but has been talked about in a few papers. But it's thought of as the idea that there are certain abilities or capabilities in models that you don't see at small scale, you see at large scale. But more importantly, I think, again, what has animated so much of the conversation is that they're hard to predict simply by extrapolating the performance in small experiments. So you run a small experiment, small here meaning small data, small model size, things like that. You look at how well a small model does in a certain task, and then you try to extrapolate what happens for large models, like we did somewhat successfully with things like, again, test loss, cross entropy. And it seems that for certain tasks, there is some trend, but when you shift from effectively zero performance to quite a bit better performance, seems to be unpredictable, specifically where this happens. And again, this ties to many larger questions the community is grappling with. So in looking at this work, we looked at a few papers tackling this topic. Details in the longer paper, but I'll just give a brief summary here. We noticed that a lot of what settings where this notion of emergent ability seems to be strongest, tied to metrics that discontinuously scaled model performance, essentially how well sort of a particular probability for next token prediction, the cross entropy. If one picked a metric that evaluated cross entropy type measures discontinuously or nonlinearly, we saw, those were the cases where we saw this a phenomenon that was called emergence, whereas if you picked metrics that were much more linear or continuous, we didn't see this phenomenon or we didn't see this phenomenon show up quite at all. In particular, when looking at Big Bench meta benchmark, we noticed that two metrics explained over 92% of the cases where emergent abilities were claimed. So this included a multiple choice metric. Here, you look at a certain task. Generally, we're doing this in settings where there's some notion of correct option. So either you ask the model to solve some kind of multiple choice, I give it A, B, C, D, pick the right answer, or things like arithmetic where the next token, there's some notion of easy evaluation based on next token error. And so if you picked, for instance, multiple choice grade, which gave a score of 1 for an example where the highest probability mass was on the right option, and then 0 otherwise. Or if you picked exact string match, very similar idea, but this is a 1 if the output string matches the target string. The main difference here in the first one, generally for multiple choice, it's in settings where just one token is enough to evaluate what the model has done. Exact strings, you need the full string. So again, things like arithmetic evaluation. Most of the notions of emergence seem to tie to these two choices of metrics. And so this led to a hypothesis that this notion of emergent abilities, and specifically the unpredictability with scale, which I think was, again, the key phenomenon that was new and interesting, might not be due to fundamentally different epiphenomena in the models with scale, but perhaps it's due to how we chose to measure, in particular, the choice of metric that may be driving what seemed to be this unpredictability. So here's the sort of the whole paper in one slide. So I start with log likelihood. Let's see if this works. Okay, partially works. That's fine. On the top, middle, A, log likelihood per token, or probability of error. They're very similarly related. Just E to the cross entropy is effectively the probability of error. And we see, again, this sort of log linear scaling trend as shown by scaling laws. And if I pick some downstream metric that is either nonlinearly scoring or discontinuously scoring, I see what looks like a sharp jump in what seems an unpredictable part of scale. So this is the left-hand side. Where instead, if I pick a metric that either linearly scores or continuously scores, I see much more standard changes of performance with scale, so on the right-hand side. And so we suggested an alternative explanation of what were called emergent abilities. We argue that there's limited evidence of this unpredictability with scale, and in fact, if we can explain via one of three factors, either choosing a metric that is discontinuous or nonlinear. I won't talk about this here, but also questions of sampling. So using very limited amounts of test data at small size, we argued was part of this notion of unpredictability. And then also evaluating too few large models. I'll defer 2 and 3 to reading the paper or offline discussion. I'll mostly focus on the first idea, this question again of metric choice. So we did a simple toy model. The simple toy model is quite naive, actually. It looks at, we take language model prediction as it's basic. I'm just predicting a sequence of tokens. Again, we'll just argue that for discussion purposes. Okay. Worse than this, I'll actually completely ignore the correlation across the sequence and just look at what is the probability of error I expect if I'm flipping a coin, and the coin has a certain probability of landing heads, for instance. And I want to look at the probability of getting a sequence of heads in a row. So a sequence of 1 head, 2 heads in a row, 3 heads in a row, and so forth. And it's something I might assign in a probability class for an undergrad course. And so very simple model, but seemed sufficient to tell the story we wanted to tell. And so on the left, I'm showing the result of this very simple model, where on the top, you pick evaluation measure that is akin to accuracy, so it doesn't give any partial credit. On the bottom, you pick an evaluation measure that has sort of a smoother or more continuous evaluation. And when we pick the discontinuous measure, we see, again, this emergent type phenomenon. On the bottom, when you pick the more continuous measure, we see much more standard linear scaling. And this replicates in a lot of the existing experimental work. So if you look at, in the middle, 2-digit multiplication, we see the exact same phenomenon. On the right, 4-digit multiplication, for the models that were released at the time, the exact same phenomenon. We're on the top, using a metric that has discontinuous evaluation, we see what looks like jumps in performance. On the bottom, if we use continuous measures, we see much more linear behavior with scale. We did some other evaluation. We looked at Big Bench, for instance, where a lot of different model families had been evaluated. And over different tasks, different metrics, different model families. And a hypothesis here was if the metric didn't matter, then you don't expect to see a strong interaction correlationally between emergence and the choice of metric. If it did matter, then changing the metric should affect emergence. So if I take a certain task metric model family triple, where there's a notion of emergence claimed, if I change the metric in the way that I just described, it's sort of pseudo-interventional, but I take something, this triple, and I switch the middle metric thing, I should predictably get from this emergence phenomenon to non-emergence. Again, explain the way I just did. And so first showing here, if we look over the big bench metrics, 35 out of 39 metrics don't have this notion of emergence built in. So again, this is a sort of small fraction of the evaluation metrics. Of the tasks where we see emergence, again, we see a similar kind of story as mentioned earlier. So multiple choice or exact strange seems to be the metric chosen. Different metrics, we have much fewer notions. There are a few which we're still understanding a bit more, things like blue score and others. Okay, so that's most of what I wanted to say about emergence. I think the paper has a few more details that are interesting beyond the metric choice, but also tied to things like sampling across scale. So again, the idea that we should sample more if we're trying to make this quantitative and also qualitative claim about what's happening with scale. Okay, switching gears a bit, I'll talk about a different paper which I think digs a bit deeper into this question. I think interesting in maybe expanding our view of this notion of metric choice affecting so much predictability of models with scale. So again, this is the paper. I hope it's up by the time we're done with this, but you know, it's been sent to archive with great colleagues across a few different institutions. And so here, I'll focus specifically, on multiple choice evaluation. So ignore for now this sort of arithmetic question. So again, multiple choice is such a big part of how we evaluate models. Again, I could give a whole talk. Maybe I couldn't because I don't understand all of it, but big complicated question of multiple choice as the notion of evaluation. A big chunk of it is we know how to do multiple choice. So if I convert an evaluation problem of a model into multiple choice, it becomes a multi-class classification problem. So I can use multi-class classification semantics to evaluate it. So but there, again, many other reasons. So you can posit a question to your model. You give it a sequence of possible solutions. You ask it to pick a token for the answer, and it gets the answer right if it picks the right token. And so, as mentioned, so much of our benchmarks actually under the hood are using this multiple choice question answering as the way that we develop evaluation. Of course, there are lots of known issues, as briefly mentioned, so things like token bias. I'll just briefly allude to this. So some work we did recently, for this work was in context of a fairness evaluation, but other folks have done this for sort of more notions, other kinds of evaluation for language models, where the specific choice of token does lead the model to sort of change its predictions. So if I flip A and B, I get different answers, for instance. We played with tokens that were letters versus numbers. We played with shapes, so special symbols that I guess get displayed as shapes. All these things seem to change the answer the model gives. I'll defer to longer discussion of this issue of token bias. But we'll take as a given this idea that we like to use multiple choice question answering as for building benchmarks. And so the key point of this paper is this claim that, again, we start from log likelihoods. Log likelihoods, cross entropy, seem to have very clean, predictable behavior over scale. Again, the scaling law idea. But when we go from the log likelihood to the final evaluation, we do a sequence of transformations. And our argument is that the sequence of transformations systematically deteriorate the correlation or statistical relationships between performance and scale. And I'll dive into this specifically in a second. So the idea is, if I look, and interestingly and meaningfully here, we're able to do this on a per sample level as opposed to aggregate over the entire data sets, which I think is also interesting, but I won't spend time on today. So I start off with loss of some model on a particular benchmark. So a particular model, particular benchmark, and I scale something, typically model size. In our example, all model size. I go from this loss cross entropy thing to a probability of error. Again, I've mentioned briefly, you can do this easily by exponentiation. So I go from the sort of loss, for an example, to probability of making the correct choice for this multiple choice question answering. Then in order to, the language model by construction is not restricted to K choices, A, B, C, D, 4 choices. It can spit out any token out of its entire token library. So many possible tokens can be the result of an evaluation. So in order to actually evaluate one of K choices, the common practice is to ignore probabilities for all the tokens and only look at the tokens for the choices that you're interested in. So probability for A, probability for B, probability for C, probability for D, to be pedantic about it. But again, just looking at those options. And so what you would typically do is go from the probability over all the tokens to just probability for the choices that you're interested in. So you do this sort of restriction thing where you ignore the probabilities and then renormalize so that it's still a probability sums to 1. And then if you're using accuracy, I pick the one that has the highest accuracy, the highest probability. It's worth noting here that there are cases where the highest probability next token is not in the correct, not the evaluation set. And so essentially you ignore the highest probability next token in order to pick the thing that's highest probability within the 4 options or the 5 options that you're interested in. And our main claim is that this choice and sequence of transformations has a meaningful effect on predictability with scale. So in math, the same thing. I start with loss. I convert this into a probability. I restrict into the set of K options that I care about, and I renormalize the probability only of those K options. Okay, and then I compute accuracy, pick the best option out of the K options, and then assign a score of 1 if I got that option right. Okay, so here's our approach to evaluating what's going on here. So we look at a particular benchmark metric and a particular example. So I'm showing, for example, model by sample. Remember, this is multiple choice question answering. So for every model, for every sample, it's either yes, I got the answer right for this particular example, so I picked the token that was the correct, either A, B, C, or D, or no, I got it wrong. So every column here is across models for a particular sample, whether the answer was right or wrong. And for models, we can look at scale. Here we're using flops. You can use your favorite notion of scale. And so we're looking at across scaling models for an example, for a particular benchmark query, whether or not the answer is right. And we can do a simple correlation between the correctness of an answer and the scale, and do this over all the different models. So this is capturing, again, this idea of how is the correctness of an answer changing with scale for a particular example, and how does this look over all the examples? Okay, so in order to evaluate this, we looked at the correlation behavior. And so most of the key results here will be tied to what is the distribution of correlations when I go through this procedure. It's worth going through sort of a cartoon of what different things one might expect if I run this evaluation. So hopefully colors show well, but the next version, I will plan to step through this. Anyways, so in red, I have a highly anti-correlated case. So this is the case where, as I scale up models, I have a sort of strong negative correlation between scale and performance. So all of the examples are anti-correlated with the sort of scaling, x-axis of scaling. In green, all the way on the right, I have strong positive correlation. So over most of the examples, I have correlations close to 1. I have middle cases. Here I have it in blue, mixed. So I have some positive correlations, some negative correlations. Yellow, you can imagine also a scenario where correlations are spread everywhere. So some examples, over examples, we have a mix of maybe uniform over everywhere, positive, negative. And then you can also imagine an uncorrelated case, so everything is close to 0. So we actually don't have signal. There's not a strong correlation between performance of models on, of particular examples across models and scale. And I'm plotting this because the way that we chose to illustrate the results, we think somewhat, well, hopefully informative. I explain this because I think in statistics, survival functions are common, not so common in machine learning, so it's useful to maybe go through this. So if I have a correlation, you can think of, if you're not familiar, survival function is 1 minus the CDF of the distribution. So if I have lots of positive correlations, I expect a survival function that looks almost like a box. If I have negative correlations, I have sort of roughly the opposite, so sort of drops down very quickly. Uniform will look almost like a line. Uncorrelated will weirdly look like a negative step function, so step down. And then the mixed will have some mix of the two things. So hopefully building some intuition for what survival functions look like. So if we want predictability, what we want is survival functions that look like the green box curve. Weirdly, but possibly the anti-correlation is also a good case. It's, highly correlated, but negatively correlated. Maybe one can dive into why, but you can imagine that to be the case as well. So hopefully this is clear. So we did evaluation over lots of model families for lots of different benchmarks. I'll leave the paper for details they might be interested in. And so I'm showing a result for a particular evaluation. So this is called the ARC challenge. And I'm showing here across different model families the PDF of correlations, so what the correlations look like across examples, and then survival function on the right-hand side. And again, we see that the log probability does seem to have roughly things that look boxy. So top right type square functions, this is the good outcome. So this is for predictability, this is the good outcome. This is what you may want. And so we did the sequence of transformations and looked at the correlation through the sequence as mentioned. So starting from the original probability of error, I see strong correlations. Here we're using Spearman, but you can use your favorite correlation statistic. Next, we apply the sort of probability step, the exponentiation step. Exponentiation doesn't change anything because it's monotonic, so things are fine. We do this normalization. What you're hopefully are noticing is all of the survival functions squashing quite a bit and getting much more close to uniform, suggesting that something is changing about the correlation between, again, this strong correlation signals that we're getting from the original evaluation. And then finally, when we look at correlation with accuracy, we see much noisier results. You can also illustrate this. This is messy. I'll attempt to step through this very quickly. So I'm looking on the y-axis over a bunch of different evaluations. On the x-axis, we picked a particular metric. Here we're looking at the mean performance overall, the examples. Different colors are different steps in the evaluation process. So they correlate strongly with qualitative amounts of correlation. So what you should be noticing, and sort of the key observation here, is that when I first look at probability of error, most of my correlations are large, all the way on the right. As I step through my computation, I first do the normalization step. I go all the way from things that on the red, all the way on the right, to the orange, which is in the middle. By the time I get to accuracy, I get to something that close to 50-50, much lower correlation across examples. The different shapes are different model families, showing that this replicates over lots of different model types. Okay, so we can do this for different statistics. We did this for mean, did this for median. Details here, not important. Hopefully the high-level picture is clear-ish. This, again, first time this is being shown. So refining it over time. Okay, so one other way to sort of dive into this observation. So on the left, I'm plotting the probability of correct choice over all the different options versus over over the entire vocabulary. On the y-axis, I'm plotting probably a correct choice, restricting only to the k choices that the model is allowed to make. Again, remember, in multiple choice question answering, I can only pick one of k tokens, so A, B, C, D. What I'm showing here, in the ideal case, I'll see a strong correlation between the two things over examples. So when I chose to restrict from all possible tokens to the k tokens that matter for my evaluation, hopefully it doesn't change the model too much, because most of the time the right token is within the sets that I'm evaluating. And what I'm showing on this plot is what looks actually to be quite weak correlation. So this is scatter plots. As a scatter plot, it's all over the place. This is, again, the key observation here is that for different probability of correct choice over the entire vocabulary, I can land anywhere and probably a correct choice once I restrict to the k options that the model can make. Showing very weak correlation between the overall probability of that the model has versus the restricted probability that the models have. We see similar things when we look at accuracy. So the key sort of maybe obvious observation is that once you have a probability greater than 0.5, the accuracy is perfectly correlated with the probability. It's not surprising, because I have a large enough probability that I'm just always picking the choice that's highest probability. But under that, the behavior is quite a bit weirder. I'm showing this over a bunch of different benchmarks. We see similar phenomenon, where the correlation is just much weaker than one would hope for trying to get at this signal. And so hopefully what some of this is showing, this sort of experimental observation is showing, is, again, we've chosen to evaluate a certain way. We've chosen to evaluate via question answering. This evaluation is done through a sequence of transformations. And the key observation here is that each of these transformations that we do to go from whatever the model initially is trained on to our final evaluation are systematically degrading predictability, which we think explain a lot of what we've observed about sort of how unpredictable downstream tests seem to be compared to the clean predictability of test error, the sort of simple probability measure. As an aside, we looked at sort of less discontinuous measures, things like Breyer score, which measures how close, roughly the quality of the probability itself. This is somewhat better behaved. So see much cleaner correlation, though it's still not perfect, but again, tying to the first part of the talk, much cleaner correlation between the probability and the final evaluation measure. Okay, so I've talked for a while, and I think slightly over what I wanted to, but the key idea hopefully is clear. So I've given a couple of examples to highlight this observation. The metrics play a key role in the predictability of performance with scale. Again, a choice of metric that's continuous seems to make predictability much harder. Continuous metrics seem to be much more predictable. And I've done this through a few different papers, mostly these two papers that highlight this phenomenon. So the first paper in particular has been out for a while. We've had lots of discussion. I'm noting the criticism not in a pejorative way, but appreciating the discussion and maybe engaging. Some of these might be questions you might ask, so I'm taking some of the question time to ask myself questions. So first is this idea. Okay, it's not that surprising that metrics affect results. Perhaps this is trivial. I think the key point here is not some general claim of metrics affecting results. I think the key point here is, again, this idea of predictability, because it ties so strongly to larger questions that we're engaging with in the field. And so, again, the observation and sort of the key phenomena we think here are important on their own merits because of this connection to predictability. Separately, and maybe offline, I think this idea of partial credits, I think is meaningful. I think it's more useful for the scientific practice. I think it's more useful for decision making, but again, I'm happy to argue that offline. Second criticism is, well, we're choosing, the metrics that we actually care about in sort of real world tasks really are discontinuous. And this idea of picking metrics that maybe are better behaved for predictability reasons, perhaps, is not really engaging with the question. I'd like to push back a little bit. I think in many cases, there are actually meaningful construct validity gaps, and the claim that we really do care about discontinuous measures. I'll just narrow down on this question of multiple choice and accuracy. I'd argue in most cases it's really a convenience choice, not sort of meaningfully engaging with what it means to evaluate what a language model is doing. I'd argue, for instance, examples of lots of doing well on various kinds of exams, which are often evaluated by your multiple choice, so things in law, things in medicine, and asking, does that actually mean that those models are useful for the downstream practice of law or medicine? And so, I think this question, is quite open and interesting. A third one, we've touched on a couple of different settings, a couple of different metrics. Perhaps we haven't touched on the metric or setting that you care about the most. We agree. And we hope that you will think of this as an interesting set of questions and maybe engage, hopefully towards this larger question of building a science of scaling predictability and understanding what is predictable, not predictable, over scale. Hopefully, again, I think much more meaningfully, human interpretability in evaluation more broadly. Okay, with that, I'll thank funders, thank my lab, Stanford Trustlier Research Lab, and a lot of students, some of which work I've mentioned over the course of the talk today. And I'll end with a quote that a student gave me, which I really like, so I'll just end here and maybe take a few minutes of questions. Unfortunately, we don't have an actual author for the quote, but I really like the quote. It says, the value of a metric is not in its measurement, but in its interpretation. Choose wisely, for what you measure determines what you see. Thank you.
Hi, thanks for the talk. I wanted to ask you about the politics of measuring intelligence. And I think I have an example for me is how we measure intelligence of non-human animals. Because despite showing like a capability for using tools, etc., they are tasty. So we focus on the discontinuity with their intelligence. And I wonder, when it comes the time to measure things such as self-awareness, to develop a benchmark for self-awareness, whether we're not going to do the same and try to focus on the exceptionalism of like human intelligence. So, and I'm also wondering if you see this politics of measuring intelligence acting now or biasing now the research.
Yeah, this is a, thanks for the easy question to start off. So I want to engage with this fully. I'll maybe touch on some points that I think are meaningful. I think it's a hard question in lots of different ways. I intentionally avoided making specific claims about measuring intelligence because I think, again, it's quite a hard question, and I don't know that we fully know what that actually means. And so we come up with these proxies that go through benchmarks. And I've argued, and many in the community have argued, I think meaningfully that there may be constructability gaps. Our choice of benchmarks and a name we give them, maybe a name that we hope will tell us, will claim something about intelligence, may or may not actually meaningfully map to notions of intelligence. I think meaningfully also, there are lots of different kinds of intelligence. Intelligence is complicated. So to your specific question of like, what will we do when perhaps things are at a stage where we can grapple more meaningfully with this question? I don't know, but I think a lot needs to change in the science part before we can meaningfully engage with that question. In particular, again, the measurement bit I don't think is quite ready. It's much more storytelling than you might think, or you might know, I guess. But yeah, so not an answer to your question, but maybe helping pushing that question forward.
Thanks for your talk. It was great the journey you took us through. I want to challenge you a bit on the idea of scaling, because of course we've seen that these models perform better just because they're bigger, because of all kinds of reasons. However, we also know that models plateau after a while, regardless of the metrics we're going to use, right? We've seen it with CPU speeds in the 60s with airplane speeds and everything. So everything that seems exponential is also like a sigmoid in the end. So I'm wondering what's your thoughts on this, also given what we see right now, that most companies moved away from, I don't know if we're going to see a GPT-5, we focus on more applications. So what's your take on this, right? Should we, I'm not saying that we shouldn't focus on metrics, but what would be also another, side, maybe task we could pursue? Thanks.
So the scaling question is, I think, a quite fascinating and important one. So on the broad question of, should we expect a plateau? I think so. I think there's a bit of hubris in expecting things will sort of continuously keep going. There's a bunch of physical laws and a bunch of things in the world that I think will constrain. Again, longer conversation, I'll leave that for offline. I think on the specifics of the scaling laws itself, this is on sort of log probability over scale. I think one, there's a sort of obvious cap because we're measuring something that's between 0 and 1, you can only go so far. That said, I think there's some gap, or at least some separation between scaling and the sort of loss, and then scaling and some downstream task. Again, the point of the talk was mostly about predictability, which doesn't engage necessarily on exactly what the patterns are. So I guess another meaningful point to your question. The bigger question is, what is the next other thing if what we care about is getting better and better models, if it's not scale? I think there's lots of discussion out there. This is a much bigger question than me. So again, thanks to everyone. Thank you for another easy question. I think there's lots of excitement about algorithmic things that might make a difference. I think the data is underappreciated. I think that's sort of a huge part of things. So big open question, lots of work there. Thank you.
So a great talk, Sanmi. I love it because I think we need to work more on metrics. But let me push on the different direction. And I think it's easier question than the others. Real things like drugs and vaccines look at harm. They don't look at success. And I think this is the big mistake we're doing in machine learning today, because when you use accuracy and all these measures, you assume that the impact of errors is exactly the same for all errors, which is never true. I haven't seen an application where that's true. For example, here you may have a completion that is completely funny, and another one is completely offensive. So have you thought about metrics for measuring harm?
Yeah, we've dabbled a little bit in this. I think the notion of metric we have here is at a slightly lower level than the question of harm, in the sense that we're looking at metric in the sense of the quantitative measure of what the model is doing, where I think the most meaningful, at least in the work that we've done, and versions of this question that engage with things like harm, are at the sort of benchmark level. So this is coupling, say, accuracy metric or whatever else you pick with sort of data set and norms that hopefully capture some broader notion of model behavior. We've done a little bit of work on this. I mentioned briefly this decoding trust paper that touched on this question. I think there's a lot more, to your point, strongly agree. I think there's a lot more the community should be doing to look at downstream impacts of models and thinking about questions of harm. So for sure, agreed.
Hi, thanks for a really great talk. The sense I get from the impact of some of the papers you've mentioned is that people previously were excited by the unpredictability, and that the papers have kind of debunked, or at least like lessened that excitement. And I want to understand, why do you think that is? Is it that people find the unpredictability to signify that we're kind of on this unknowable kind of journey towards superintelligence, and that these papers have kind of dampened that hope or that hype? Is that what you think is going on here?
Yeah, this is an interesting question. I would say it's actually quite hard to segment purely by sort of subcommittee and what people care about in terms of how to engage with this question. I would say, to the first order bit, I think you're right, that a lot of the initial excitement about emergence was, again, the sort of unknowable unknown. To your point, I would also say that part of our work isn't saying, we're partially closing the gap. We're also saying that there are notions of unpredictability that remain, but we think they're easily fixable, and maybe they tie to sort of bad measurement practice. And if we have better measurement practice, we have better predictability. It's maybe an important aside. I would say different communities have engaged with the outcomes of this work, actually. Some, again, much more directly on the critique of unknowable, unknowable. I think also communities are interested in, like, if you can predict, what does this mean downstream for sort of, again, notions of intelligence at scale. So it's actually quite hard to fully separate who thinks this work is most important. But I would say your first order point does seem true. Like the pure surprise version, I think this work has dampened a little bit.
All right, let's thank Sanmi for the talk, and I agree that we should all learn more about measurement modeling, measurement theory, and constructability. And you will find him in the coffee break. Thank you all.